So hi everybody, my name is Romain Basalgète. So I'm a last year PhD student at the l'ERMA working with Mathieu Bertin and Jean Fillon. And so today I will focus on experiments on X-ray photodesorption from molecular ices. So X-ray photodesorption is a process occurring in a dense and cold interstellar medium. In these regions, you have a solid phase and gas phase, and you have constant exchanges between these two phases. Okay, molecules from the gas phase can condense on the cold ices, and molecules on the ices can be ejected in the gas phase via non-thermal desorption processes. And if you want to understand the chemical evolution of the interstellar medium, you need to understand these non-thermal desorption processes. And one of these processes is the desorption induced by X-rays, which is called X-ray photodesorption. And it is especially relevant for protoplanetary disk because the young star at the center of the disk can be a strong X-ray emitter. So previous studies on X-ray photodesorption have shown that X-ray can indeed induce desorption of various species, for example, from pure water ice or pure CO ice, which was studies conducted by the l'ERMA group. And also other groups have conducted experiments for more complex ices, and they have also shown that X-ray can, in that case, also induce desorption. And more recently, there have been modeling studies by Notsu that have shown that X-ray photodesorption can significantly influence gas phase abundances of water in protoplanetary disk. So this further encouraged to conduct additional experiments on X-ray photodesorption. And so today, I will try to answer two questions. The first one is, what's the fundamental mechanism of X-ray photodesorption? And the second one, which is quite important, is X-ray photodesorption efficient for complex organic molecules, and especially for molecules that have been detected in a protoplanetary disk? So the approach retained is purely experimental. In an ultra vacuum setup, you grow molecular ice on a cold substrate. You irradiate the ice with X-rays coming from, so in that case, the studies were conducted at the Soleil synchrotron facility on the Sextant beamline. And you probe photodesorption directly in the gas phase by mass spectrometry. And from the mass signal, you can deduce photodesorption yields, which are expressed in molecules desorbed by incident photon, and which quantify the efficiency of a photon to desorb a given molecule at a given energy. And so we study these yields as a function of the photon energy by varying the incident photon energy. And especially, we have studied X-ray photodesorption in the soft X-ray range between 400 and 600 eV. And we also want to study the effect of the ice composition on the yields. And as I will show you later, the ice composition can have a significant impact on the desorption yield when it comes to complex organic molecules. So we first present X-ray photodesorption for a simple system, a mixed ice of CO and N2, where CO and N2 are in similar quantities. So the interesting fact about this system is that you can excite either CO or N2 in different energy range. For instance, N2 is expected to dominantly absorb in near 400 eV. So here in blue, you have the absorption spectrum of N2, which is dominated here by N2 resonance that correspond to the promotion of one s electron to an empty molecular orbital. So when you irradiate the ice in this energy range, you selectively photoexcite N2, and you observe the desorption of CO. And the desorption need of CO as a function of the incident photon energy is exactly matching the N2 absorption spectrum. So it means that clearly X-ray photodesorption is an indirect process in a sense that when you photoexcite one molecule, you observe the desorption of other molecules from the ice surface. And one question that you can ask is, what is the maximal distance at which you can photoexcite one molecule in order to induce desorption from surface molecules? And in order to estimate this distance, we did additional experiments, which are the following. So we first grow a thick N2 ice, on the top of which you deposit one monolayer of CO. You irradiate the ice at the N2 resonance to excite N2, and you probe the desorption of CO. You repeat this experiment by sequentially deposit one monolayer of CO at each step and irradiate to probe desorption, such that you can plot the desorption need of CO as a function of the number of layers of CO on top of the N2 ice. And this allows you to estimate this maximal distance. So here you can see that in the low coverage regime, you see that the desorption yield is linearly increasing, and then you have an exponential decay. And from this, you can deduce that the maximum distance at which the indirect desorption can occur is approximately 30 to 40 monolayers. So the question now is, what mechanism can explain this behavior? And one of the possible mechanisms is the Auger scattering. So when you excite N2, you induce a core electronic transition, and the decay of the core state results with a probability close to 1 to the emission of a valence electron, which is called the Auger electron, and which carries away most of the energy of the incident photon. And so these Auger electrons will scatter towards the ice, and they will eventually scatter towards the ice surface to induce desorption. And if you want to understand if this Auger electron is indeed explaining this behavior, what you can do is try to estimate, what is the energy, the amount of energy deposited by this Auger electron at the top layers. And fortunately, you can easily estimate this amount of energy thanks to this study, where they showed that the energy deposition profile of such electron in the N2 ice can be approximated by Gaussian distribution in one dimension. And so with this energy deposition profile, you can easily estimate the energy deposited on top by summing the contribution of each layer of the N2 ice. And so you do this computation as a function of the number of layers of CO on top, and you obtain this amount of energy deposited by the Auger electrons. So you can see that this energy, this simple computation is quite in good correlation with the yields for this high coverage regime, but not for the low coverage regime. But if you consider that in this regime, when you deposit CO, you do not make an homogeneous deposition, but actually in this regime, your surface is more is composed more of a mix of N2 and CO molecules, such that you need to actually sum the desorption need of N2 and CO, and in that case, you obtain a very good agreement between the energy deposited by the Auger electrons and the desorption yields. So these results strongly suggest that indeed X-ray photodesorption is driven by the scattering of the Auger electrons. So with this simple system, we have shown that in the interstellar medium, the X-ray photodesorption can be induced by any molecules, photo-absorbing molecules in the ice. And the molecules involved in X-ray photodesorption are the molecules that are contained in the first few tens of monolayers of the ice for the soft X-ray range. But this distance is expected to vary with the photon energy. And so now the question is, what is the role of this Auger electron, and what is the role of X-ray photodesorption for complex organic molecules in protoplanetary disk? So we have conducted experiments on complex organic molecules by studying two systems. One ice where the complex organic molecule is mixed with CO ice, and one ice where it is mixed with water ice. And these two ices are supposed to represent different physical conditions of the interstellar medium. The water ice is expected to represent, let's say, cold regions where the ice temperature is between 90 and 20 Kelvin, such that you expect to have mainly water and small quantity of complex organic molecules. And the CO ice is more representative of a very cold regions where you expect to have a CO freeze out, for ice temperature below 20 Kelvin, and that can also contain some small quantity of complex organic molecules. So we irradiated these two ices at 560 eV, and we look at the desorption of the intact complex organic molecules. And this is what we observed. We see that when the complex organic molecule is mixed with a CO ice, we indeed detect its desorption with a yield close to 10 to the minus 3 molecules per photon. But when the COM is mixed with water ice, we do not detect its desorption anymore. It is under our detection limits. So this is quite interesting results, because first we have shown that X-ray photodesorption can indeed participate into gas phase abundances of COMs in the cold disk. And the data show that the efficiency of such process should be dependent on the ice composition. And so the question that you could ask is why we observe this behavior. And one possible explanation is the chemistry induced by the Auger scattering. So for methanol, if you look at previous studies on the X-ray irradiation of methanol water ice, the studies by Krim and Lafond, they showed that the chemical reaction can be summed up by these reactions, where the major radical that's playing the major role is OH radical. And this chemical network is very consistent with our photodesorption data, because when we mix methanol with water, we do not see it desorbing, which could be due to its chemical destruction by its reaction with OH. And instead, we see the desorption of radicals that could be associated with CH3O or CH2H, which is consistent with the products of this reaction. And also, when you look at the desorption yield of CO versus CO2, in pure methanol ice, the CO desorption yield is higher than the CO2 yield, but in the mixed water methanol ice, it's the opposite. The CO2 yield is higher than the CO yield, which is consistent with this last reaction. So it seems like the reason why we do not see methanol desorbing from water ice can be due to its chemical destruction by its reaction with OH, which competes with its intact desorption. And the same story can be deduced for acetonitrile. When you look at the total electron yield, which represents the molecular composition of the near ice surface, here you have the feature associated with acetonitrile, and you look at the variation of this feature with the photon fluence. So you see that when you irradiate the ice, this feature decreasing, meaning that you dissociate acetonitrile, but still with a high photon fluence, you still have a significant presence of acetonitrile near the ice surface. But when you look at this feature for water ice, you see a very fast decrease of the acetonitrile feature and growing of other features. So this clearly shows that when acetonitrile is mixed with water, you very fastly destroy it. Okay, and one of the photo products that results from this destruction is here can be associated with N2. And so similarly for the case of methanol here, what is suggested here is that acetonitrile is the reason why we do not see acetonitrile desorbing from water ice can also be due to its chemical reaction initiated by the water ice. For formic acid, it's not the same story. When you look at the variation of the dissociation of formic acid with the photon fluence, you do not see any significant difference in the destruction kinetic, whether you are in pure ice or in CO or water ice, which can be simply due to the fact that the dissociation of formic acid is very efficient already by photons and electrons, and that the chemistry does not play a very significant role here. And so the reason why we do not see formic acid desorbing from water ice can be due to, for example, different adsorption energy at the surface of the water ice. So to conclude, we have shown that X-ray photodesorption is an indirect process driven by the Auger scattering, and that the chemistry induced by this Auger electron can influence the desorption of complex organic molecules. So we have shown that the data show that X-ray photodesorption should depend on the region considered, namely in protoplanetary disk, beyond the CO snow line, X-ray photo desorption of complex organic molecules should be weaker than the same processes beyond the CO snow line, where the complex organic molecules are mixed with COs. So here the studies were conducted in a soft X-ray range, but the X-ray energy can go up to 10 keV, so additional experiments should be conducted at this higher energy. And especially in protoplanetary disk, there are multiple other non-thermal desorption processes, for example, UV photodesorption or cosmic ray sputtering, that can play a role for the abundances of COMS, and such that we need disk modeling that incorporates the different non-thermal desorption yields to deduce if there is a dominant mechanism that can explain the presence of COMS in disk. Thank you for your attention.